Welcome, everyone. This is going to be a public discussion for chip number 11. We are going to talk about these BLS additions that have been proposed to add to the CLVM. And we have with us Cameron Cooper, who wrote the chip, and Freddie, who is also interested, and I am Dan Perry, and I'm a technical writer here at Chia. I'm helping to get this chip organized. So Cameron, why don't we get started? And can you just basically explain what, at a very high level, what BLS is and why we're using BLS?
Yeah, so we use BLS to create signatures in Chia. And so whenever you have a coin or do a spend, a lot of times that's verified that you own that coin by creating a signature using your private key, and you attach that signature to your spend, and then it goes into the mempool, and the farmer will farm a block. And one of the things they do when farming a block is they actually aggregate all of those signatures together to produce a kind of unified block of all of the spends. And one of the great properties of BLS is that it makes it very easy to aggregate signatures. And so while BLS isn't commonly used in blockchains today, it's becoming more common. I think for one of the reasons is that easy aggregation. And so BLS is really fundamental to the way Chia works. Chia wouldn't be able to work the way that it works without BLS. And so if you are familiar with Chia Lisp and have looked at some of the built-in opcodes in CLVM, we already have a couple of BLS related opcodes in there. We have point add, and we've got pubkey for exponent. And so those are useful for creating G1 points. So BLS, and I'm going to kind of avoid a lot of the sort of deep dive into sort of cryptography, but basically, BLS has points on a curve is a simple way of describing it. And there's multiple curves. There's two of them. And so the first one would be what we call the G1. So a point on that is called a G1 point, and then a point on the corresponding other curve would be a G2 point. In Chia, we use points on the first curve, the G1 points, as keys, and we use points as on the G2 curve, or the G2 points are signatures. And so what this means is those two ops that we already have, the pub key for exponent and point add, it allows us to do basic G1 operations. And if you've read our standard transaction, you'll see that we actually use that to create these synthetic keys where we actually kind of add them together. And this allows us to have those hidden puzzles. And this is how we do all that kind of taproot neat functionality that we've got. And so the point of this chip is actually to augment our BLS support within CLVM. So we had those very basic ones for creating a G1 point and for adding two G1 points together. That gave us what we needed for the standard transaction. But there are a lot of other things that we do in BLS outside of CLVM, and we do it at the wallet level. And we may want to be able to do some more things on chain in Chia Lisp and in CLVM, and that's the purpose of adding these new codes. And so at its sort of core, most of the BLS operations are just like math operations. And so you want things for the G1 points and the G2 points, you want to be able to do basic math operations. You want to be able to add them and subtract them, multiply them. And so so the first thing that this chip does is adds additional sort of operations for all of those G1 points and the G2 points, where you could do additional math operations on them. And then we also then added the pairing functionality, which is this is how you get into creating a signature from your key. If you've got a message and you want to make a signature using your key, you do a pairing operation. And so that's another thing that we had to do to pair those curves. And so we've added a pairing function. And then finally, the output of the pairing is actually what they call a GT point. And so we also needed all of the same add, subtract, multiply, and negate, just basic math primitives for GT points as well. So it's really kind of three main, or maybe four buckets of operations that we want to add to CLVM here. There's the G1 operations, there's the G2 operations, and the GT operations, which are all just basic math operations, the add, subtract, multiply, and negate. So we've done that for G1, G2, and GT. And then we've added pairing, which allows us to create a signature. And then in support of that, we've also got this, which Dan is showing here, BLS map G1 and map G2. And this is important because you need to be able to get a G1 or a G2 point from arbitrary data. And so this BLS G1, map G1 and map G2 operations will allow you to take data and actually map it to those curves and to be able to get one of those points. And that's how you can do something like, I've got this data and I want to make a signature for it. Well, then you would actually just map it. And then you've got a point that you can do these pairing operations on. So I know it's a little bit complex there, but I'm trying to keep it as high level as possible. But yeah, the whole spirit of this was augment the BLS capabilities that we have within CLVM so that we can do additional cryptographic operations in CLVM. And those may be things like generating signatures or verifying signatures, which is something that we're not able to do on chain before, but we could actually do that once we have these operations. We would be able to do that in Chia-Lisp. And that's useful for a number of applications. One of them, which we're interested in, is being able to do zero knowledge proofs. This is something if you wanted to have like an L2 that used zero knowledge proofs, you would need to be able to produce a proof that could be verified in Chia-Lisp. And right now we don't have the opcodes to allow us to do that. And that's what this chip would provide. So while this chip, the main goal is not just to support zero knowledge proofs, but that is a very welcome outcome of this. It's something that we want to be able to do, but without that, we still need to have all of these additional capabilities for other things that we would like to see built too. So I know I said a lot. Hopefully that was a fair enough intro, and if you have any questions or whatever.
No, thanks for that detailed introduction to this chip, Cameron. Really appreciate it. I think my next main question is this fairly comprehensive as far as what exists in BLS today that we want to add? Do you foresee any more operations that we would need to add?
Yeah, great question. I think this is comprehensive. And so this is comprehensive in terms of the math operations that you can do with BLS that you might want to do. And then I think it also supports all of the sort of commonly seen operations that we use or that we've seen used for doing things like creating signatures or verifying signatures. And then also, like I said, we would like to be able to see this support zero knowledge proofs. And so, I've gone through and looked at some zero knowledge implementations just to make sure that all of the things that they're doing, we would be able to do. And it looks like, yeah, I don't, there's nothing else that's on my radar that is once we do this, we need to go and add that later. I think that this is pretty comprehensive. At least that's the intention.
Okay. Yeah, that's good to hear. And how would this get added to the CLVM? Is it just the standard soft fork?
Yeah, great question. Yeah, so at the deepest levels, these are new operations that are added to CLVM, and so they all have new opcodes. And so you can invoke those operations by using those opcodes. They do need to be, we do need to manage the rollout of it, right? Because these are ops that do not currently exist on mainnet. And so, yeah, we need to wrap those in a soft fork to make sure that they're only accessible, and then we can sort of maintain backward compatibility and manage the rollout here. So, yeah, we will have to soft fork these in. But yeah, hopefully that'll be pretty straightforward to do.
Yeah, and for those not familiar, there is an operator within CLVM that's called soft fork that allows us to do exactly this, and that was created specifically to add new functionality to CLVM in a fairly easy way.
Yep.
All right, so I take it we would have to pick a fork point, and that would be when the soft fork occurs, and so this would be kind of a standard soft fork where these new operators would be accepted only after that point. Is that how it would work?
Yeah, that's roughly how it would work. We haven't gone through kind of the whole sort of release planning and rollout management here, but that's that's essentially how it will have to work. Is we'll pick a block height where these ops become active, and then at that point, you'll be able to use the soft fork operator and invoke them.
Okay, and then so this chip is not actually for implementing any, or it's for implementing these operators, but not anything on top of them, right? Not using anything with them. It's just simply getting them into the
That's right.
language so other people can use them.
That's right. There is a reference implementation added here. So if anybody who's interested in building these could start to build something using these, and I'd love to see work on that start as soon as possible. That was one of the motivations for building this reference implementation. But yeah, we already do have code that has all of these operators implemented. Anybody who's interested could actually start to use CLVM with all these BLS ops in them, and whether it's creating and verifying signatures or working on zero knowledge proofs, that's something that can all be worked on today. Obviously, it's not live on mainnet, but it's something you can start making progress on.
Okay, where should people go to find that?
Hopefully, if it's not linked here, we should add. There's a link to it. We've got a branch in the CLVM RS repo.
Oh, I do have it here. Yeah.
Yeah.
Okay, so it's in this reference implementation section.
That's right. Yep. So there's a branch in there that you can use.
Great. So people can go play with it.
Exactly. So that's the implementation of all the BLS opcodes. You'll likely want to be able to use CLVM tools RS to be able to compile ChiaLisp down to this new CLVM code. I also have a branch, which is not linked here, for adding just the mnemonics to the ChiaLisp language. So you can actually just, because we've listed the names of these operations here, but those aren't built into CLVM. They actually, at the CLVM level, they have opcodes, which is just a number. If you want to call BLS pairing, that's a compilation step that's done by CLVM tools, the ChiaLisp compiler, to compile it down to CLVM. So you may want to use the forked version of, or the branch on CLVM tools, the ChiaLisp compiler as well.
Okay, and so you've already picked out the codes or the numbers that these will map to? Oh,
Yep.
okay.
So
okay.
those are all in the CLVM RS repo, that branch that you showed below. But if you want to write ChiaLisp using these names that compile down to that, then you need to have a modified version of the compiler that has these names in it. So just so everybody understands, there's the ChiaLisp compiler is separate from the CLVM sort of engine. The CLVM engine now has a branch with these new ops added into it. But if you want to write ChiaLisp code using these new names, that's a separate project that has these new names added to compile into it.
Oh, okay. Would you consider that to be part of this chip too?
You will from a practicality perspective, we will release them all at the same time. You wouldn't necessarily use the CLVM changes without an updated compiler that had those opcodes in it. But yeah, this chip was really just about describing the new ops that we wanted to add to the VM.
Yeah, it makes sense, because you could have other languages other than ChiaLisp in theory to compile down to CLVM. So this is just a CLVM layer. Okay, that makes sense. And Freddie, you had a couple of questions.
Yeah, I've got two very simple questions. The second one I think you basically already answered. The first question was just whether adding G2add, whether that's the same thing as signature aggregation, which I think it is. And
that's the great thing about BLS, is that when you've got signatures and you want to aggregate them, you literally just add them together, which is just super neat.
Yeah, it's very simple. Yeah, the other one was I get you did mention you can verify signatures as well. So I guess that's a case of writing a function in ChiaLisp which calls these operators in a certain way, and then you'd be able to verify.
Yep, that's right. So I can try to describe how the verification process works, but the easiest thing to do is actually just go look at an implementation. So if you could pop open our BLS signatures library, you can see the C implementation that essentially would do what this is doing, which is call underlying BLS math operations, where it'll do some it'll map to a G1 point, or a G2 point, and then it'll do a pairing, and then it'll do just a couple basic operations. And so you can see the kind of algorithm there. And you can also go and look at the BLS spec and learn there how to do it as well.
Cool, thank you.
Yep.
Great, thanks. I think that basically covers the whole chip. It's a fairly simple thing, at least on one level, is just adding these operators to CLVM, and we've covered the whole thing, I think. So going forward, this chip is already open. It is currently, let me go to the top here. It is a draft, and it'll be in draft mode for a little while while we get everything implemented underneath, and eventually we'll move it to review and call for reviews on it. And if, assuming everything looks good and we have consensus from the community, then we'll put it into last call for 2 weeks. And assuming nothing changes, then it becomes finalized. Do we have a rough idea on the time frame of like how long we expect it to be in draft?
No, I think part of that will depend on any feedback that we get from the community. If we get feedback that there's desire for additional operations or changes in any of the parameters, then that's something that could extend the amount of time this is in draft. But if the feedback's all good, no changes necessary, then this could be ready to go pretty quickly.
Great. Okay, thanks. So that's where you guys come in. If you're watching this later, if you have any requests for modifications or comments to make or just clarifications, hit up Cameron or me. We're both on Keybase. I'm going to put a link to this video on Keybase, and then the chip itself is in our chips repo on GitHub. And so you can go into there and leave your review. Okay, thanks guys for taking your time to do this, and take care.
Thank you.